Okay, now let us see some more applications or problems which will help us in understanding the definition of continuity in a better way. So, let us take this following problem. Suppose f is a function from R to R. Also assume that f is continuous at all real number x. So, this is the assumption of the function, it is continuous everywhere. Suppose f x is equal to 0 for all x in the set of rational numbers. Okay. Then question is, what is f? So, the meaning of the question is, what is the value of the function at all points which are irrational? That is, what is f x if x belongs to R minus q? That is the question we are asking. So, let us see how to solve this. See, there is something involved here about the rational numbers. What do we know about rational numbers in real line which is going to help us here? Well, rational numbers has the following property, that they are dense. Means what? It means you take any real number, call it x naught, then there exists a sequence of rational numbers which converges to that real number. That is, we know that given any x naught in R, there exists a sequence Rn which is contained in Q such that Rn converges to x naught. Now, the rest is really simple. I know that f is continuous everywhere on real line. It means in particular f is continuous at x naught, and since Rn converges to x naught, I know that this implies that f of Rn converges to f of x naught. But what do I know about f of Rn? It is given to us that f of Rn is 0, because f is 0 on the set of all rational numbers. So, this implies the constant sequence 0 converges to f of x naught. But a constant sequence always converges to the same constant. So, this implies f of x naught is 0. It means in particular f x is 0 if x belongs to R minus q. That is, f is identically 0 function. Now, before proceeding any further, let me first make some definitions. The point is, so far we have discussed only about continuity of functions at points. Now, I want to talk about continuity of functions on sets. So, the definition you will see what I am going to make is a very natural one. So, let f be a function from domain of f to R. F is called continuous on the set domain of f, which is certainly a subset of real line, if f is continuous at each and every point of the set domain f. Okay. If f is continuous at all x in the set domain of f. Okay. That makes sense. For example, suppose I define the function f from 0 1 to r given by f x equal to x square. Then what is domain of f? The way I have written, the domain of f is 0 1 and f is continuous on domain of f, because we know that f x equals to x square is continuous at each and every point of 0 1. Okay. Now, from now onwards I will be only interested in the cases when domain of f is an interval. It might be an open interval, might be a closed interval, might be semi-open interval, but always it is an interval. Sometime it might be even whole real line also. Okay. So, domain of f, I will assume so far that domain of f is equal to interval, a finite interval, or whole real line. And with all these assumptions, there are essentially two results on continuous functions which come quite handy and have far reaching implications. The first one, which I am going to talk about now, deals with the case when domain of f is a finite closed interval. Okay. So, that is the first theorem I am going to talk about now. So, let f be a function from closed interval a b to r. If f is continuous, then f is a bounded function. What does a bounded function mean? It means this, that if you look at the collection of all f x's as x vary over the closed interval, then those f x's, they also lie inside a closed interval. Okay? That is, f is called bounded if there exists some m bigger than 0 such that mod of f x is less than or equals to m for all x in the closed interval a b, which is same as saying that the collection of all f x's where x in the closed interval a b is contained inside the set minus m m. Okay? That is, in the picture it will look something like this. that this is A, this is B. Okay. Suppose this height is m and this height is also m, then the graph of the function won't cross this line. Okay. This is what a bounded function means. So, shall we see an example of an unbounded function? Well, if I look at this, say that domain of f is open interval 0, closed 1, and I define f x equal to 1 by x. Okay. Then what happens is, if you draw the graph of the function, it will look something like this. This is 0, this is 1. Okay. The graph of the function looks like it goes on and on and on, you know, it never touches the y axis. So, this is certainly an unbounded function, because given any real number I can actually find an x as small as I like, so that 1 by x is bigger than that real number. It follows really from the Archimedean property. Okay. So, unbounded functions do exist, but the thrust of the theorem is that if f is continuous and the domain of f is a closed interval, then f has to be a bounded function. Notice that in my example, the domain of f which I have taken is not a closed interval. Okay. Now, that is just one part of the theorem. The second part says f assumes its bounds also. What does that mean? It means there exist x naught, y naught in a b such that f of x naught is less or equal to f x which is less than or equals to f of y naught for all x in closed interval a b. In this case, you can certainly see that f x actually lies between two lines whose heights are f x naught and f of y naught. Okay. So, let us try to prove the first part first. Well, the idea is to use the contrapositive argument, that is, you assume that f x is not bounded. Okay. So, if possible, let f be an unbounded function. What does this mean? F is not bounded. Well, f bounded means there exists a number m, a real number m, such that mod of f x is less than or equals to m. It is not bounded, that is unbounded. It means what? It means whatever real number you take, there exists an x in closed interval a b such that mod of f x is bigger than or equals to that number, right. In particular, then it is going to happen that if you take any natural number, let us say n, then there exists a number x in closed interval a b such that mod of f x is bigger than or equals to n. and I can call that x xn. So, let me write it down. Then given any natural number n in n, there exists xn, a number in the closed interval a b which depends on n, that is why I am writing xn. Okay. There exists xn in the closed interval a b such that mod of f x n is bigger than or equals to n. Okay. Notice that in one stroke I got two sequences. One is the sequence of xn's which is lying in the closed interval a b, and I got another sequence f x n, okay, which is an unbounded sequence. So, first consider this sequence x n. This is contained in a b, and the sequence f x n is an unbounded sequence. Fine. So, what do I know about xn? Xn is a sequence which lies in the closed interval a b. That means, in particular the sequence xn is a bounded sequence, right. So, let us note that xn in particular is a bounded sequence. Now, let us recall Bolzano-Weierstrass theorem. What does it say? It says that every bounded sequence has a convergent subsequence. If I concentrate on the sequence xn which I have constructed, it is a bounded sequence. So, by Bolzano-Weierstrass theorem, it will have a convergent subsequence. Call that subsequence xnk. So, this implies by Bolzano-Weierstrass theorem there exists a subsequence xnk which certainly is contained in AB. Okay. Since this is convergent, assume that it converges to some number x naught. Okay. Then I claim x naught is also in the closed interval AB. Why so? Because if not, then there exists epsilon bigger than 0 such that x naught minus epsilon, x naught plus epsilon intersection closed interval AB is null set. This is one property of closed intervals I am using. Pictorially, what I mean is just that suppose this is A, this is B, and x naught is not in this closed interval, means it might be somewhere here, it might be somewhere here, but whatever it is, it will have some distance with A or B. So, exploit that distance. You can manage an epsilon such that you get this interval, or you have this interval around the point which does not intersect the closed interval. But then this implies there does not exist any nk such that xnk belongs to x naught minus epsilon, x naught plus epsilon, because the all elements of the subsequence xnk are actually contained in the closed interval AB, and I have got an interval which is outside the closed interval AB. So, the xnk's which I was looking at, they cannot be in that interval, As a result, this then implies that x n k does not converge to x naught, which is a contradiction, because I know that the subsequence x n k converges to x naught. So, I have established that x naught belongs to the closed interval also. You will see why it is important, because somehow I want to exploit the continuity of the function which is given only on the closed interval. Once I guarantee that x naught belongs to the closed interval a b, I can use the fact that f is continuous at x naught. This is why we are trying to show that x naught belongs to the closed interval a b. Okay? Well, since f is continuous at x naught, that I know because now x naught belongs to the closed interval. This implies by definition of continuity now that f of x n k, if I look at this subsequence, this converges to f of x naught, correct? Because since x n k converges to x naught, f is continuous at x naught, f of x n k certainly should converge to f of x naught. But now we anyway know that every convergent sequence is a bounded sequence, and f of x n k is a sequence which is converging to f x naught. So, it is a convergent sequence. So, in particular it is a bounded sequence. So, this implies the sequence f of x n k is a bounded sequence. But by construction of the sequence x n, I know that mod of f x n k is bigger than or equals to n k. This follows by construction. So, on one hand I have that the subsequence f of x n k which I have constructed is an unbounded sequence anyway. On the other hand, using continuity of the function, I get that the sequence f of x n k is a bounded sequence. Now, a sequence cannot be bounded at the same time unbounded. So, that is a contradiction. And why did this contradiction happen? This happened because I assume that f is not bounded. So, this is a contradiction. So, we have a contradiction. Which implies that f is a bounded function, which is precisely what we wanted to prove.
So, what we have proved in the first part of the theorem, let us see again. We have proved that suppose f is a continuous function from closed interval a b to R, then f is bounded. That is, the set x which is equals to f y, where y belongs to a b, this is a bounded set. Okay. Now, the second part of the theorem was to show that f attains its bounds. So, what does that mean to show? That is, let us say that supremum of the set f x, where x belongs to a b, let us say this is equals to capital M. I know that the supremum exists, that is by the first part of the theorem, right, because the set of the values of f, that is a bounded set. So, it does have a supremum, call that supremum f. We want to prove that, there exists x naught in AB such that f of x naught is equals to m. Now, how do we propose to show that? Well, the only weapon we are going to use is the definition of the supremum. Okay? Fine. So, choose some natural number n in N, and then consider the number m minus 1 by n, which is strictly less than m. That means, since it is less than the least of the upper bounds, that means this number m minus 1 by n is no longer an upper bound. This implies there exists some xn in AB such that m minus 1 by n is strictly less than f of xn, which is less or equals to m. Okay, good. This in turn implies that mod of f of xn minus m is strictly less than 1 by n. So finally, I have managed a sequence because this is happening for every n. Now, where do this sequence xn lie? I know that it is actually contained in the closed interval AB. That means it is a bounded sequence. This implies, by Bolzano-Weierstrass theorem, there exists a subsequence which I might call xnk now, which is convergent. That is, it converges to some x naught. And notice, since the whole sequence inside the closed interval AB, the limit of the sequence also has to be in the closed interval AB. It cannot go outside. This kind of a logic we have used before also. Now, this implies, by continuity of f, now we have that f of xnk converges to f of x naught. You must have guessed by now that I want to prove that f of x naught is equals to m. So, how do we propose to show that? Well, this is where I am going to use this inequality. What does this inequality tells me? It tells me that mod of f xnk minus m is less than 1 by nk. Now, this implies if I take the limit as k going to infinity, what do I get? I get f of xnk minus m, this is less or equals to limit k going to infinity 1 by nk, and I know that the right hand side limit is 0. So, I put 0 here. But now, if I use the fact that modulus is a continuous function and f itself is a continuous function, it then implies that mod of limit k going to infinity f of xnk minus m, that is equal to 0. This certainly implies that limit k going to infinity f of xnk, which by continuity is f of limit k going to infinity xnk, which is equals to m, from this inequality. Okay. But then this implies, as this quantity is actually f of x naught, I have that f of x naught is equals to m. That means the upper bound has been achieved. Certainly that is not the end of the proof. The next step would be to look at, let us say, little m equals to infimum of fx with x in AB. And then exactly as in the previous arguments, I can show that there exists y naught belongs to AB. The proof is exactly similar. You can try it this way, such that f of y naught, that is also equals to m. That means the supremum of the values of fx, which is the best possible upper bound you can have, is actually f of x naught for some x naught. Similarly, the infimum of the values of fx, which is the best possible lower bound which you can have, is actually achieved by some value y naught in AB, such that f of y naught is m. Now this finishes the proof of the result. So what we have proved? We have proved that if I have a continuous function on a closed interval AB, then first of all the function is bounded. That means there is a height, okay, you can view it this way, that this is the plane R2, A is here, B is here. If f is a continuous function on closed interval AB, then all we are saying is there exists a height here and some height here. I might call this height m and this little m, and then I draw these lines. Then f is bounded means that the graph of the function over this closed interval AB lies within these two lines. That is, the graph of the function has to be something like, it cannot cross these two lines which I have drawn. Okay, that is what boundedness of a function means, and it achieves the bounds here. Well, maybe I will put this height a bit up. It achieves the value m not here. The corresponding value is x naught. Here it is x naught, this is y naught. Okay, that is what the theorem actually means. Now let us go to the next important property of continuous functions on intervals. This is called the intermediate value property. In short, we call it IVP. Okay, what does the statement say? Suppose, just look at this kind of an example. This is again the axis. Suppose I have a point A here, I have a point B here. Suppose at the point A, f of A is negative, that is, the value is somewhere here. And suppose at the point B, the value of f is positive. Now f is a continuous function. It means if I can draw the graph of the function, then I can draw it without any break. That means in the graph there is no break. Now if you have to do it that way, that means you have to join this point and this point through a graph which has no break, then it is obvious to see that the graph has to look something like this. It might be something like this also, I don't care. Without any break I am drawing the graph, but that means there is some point on the x-axis which is the value of fx. For example, this point, this point, this point. That means there exists some x in that interval where the value of fx is 0. The intermediate value property actually generalizes this. What does that say then? Let us come to the precise statement of the theorem. Suppose f is a continuous map on an interval. Now I can be closed, it can be open, semi-open or semi-closed. While doing the proof, you will notice it is only the closed interval which matters, but the result is true for any interval. What does it say? Suppose A and B are 2 points in I with A less than B. Let FA also satisfy the condition it is less than FB. Okay. Now you just consider any number between FA and FB. Consider some C which satisfies then I want to say there exists some x naught which satisfies A less x naught less B such that f of x naught is equal to C. It just means that between two functional values, if you take any real number, that real number itself is a functional value. That is what intermediate value property says. Okay. Now to prove this, we will essentially do a special case, and we will see from that how does the usual proof follow. Okay. So let me assume first that I have a map F from closed interval AB to R. It satisfies two conditions, that FA is strictly less 0 and FB is strictly bigger than 0, and F is continuous, of course. Fine. The claim is, then this implies there exists x naught in AB such that f of x naught equal to 0. The thing to notice here is that if you look at FA and FB, FA is a negative number, FB is a positive number. So 0 is a number which lies between these two. And then what I am trying to show is that there exists a point x naught so that f of x naught is equal to 0. That is almost like intermediate value property, right? There is a value which is intermediate between FA and FB, then that value is actually a functional value. That's what we are planning to prove. Okay. So let us try to prove this first. How do I prove? First, let me consider a set E, which is collection of all x in AB such that f of x is strictly less than 0. Notice that this is a subset of AB, because all the x which I am taking, they are from AB. Okay. Now notice that this set is certainly non-empty, because A belongs to E, because FA is given to be strictly less than 0. That means this set E which I have constructed is a non-empty set and it is bounded above. Means this set E must have a supremum in R. So this implies, call that supremum C. Now also notice that since E is contained in the closed interval AB, the supremum of E is anyway lesser or equals to B. At the same time, it is also bigger than A because A belongs to E. This implies this C actually belongs to AB. I wish to show that f of C is actually 0. Okay. Now why is that so? Now since C is supremum, this implies there exists a sequence xn which is contained in AB, and also xn converges to C, that we have observed before. Now this implies by continuity that f of xn converges to f of C. Now I also have that f of xn is strictly less than 0 for all n. What does this imply about the limit? if I have a sequence all whose terms are negative, then the limit of the sequence cannot be positive. At the most it can be 0. So this implies then that f of c is less or equal to 0. What I need to show is f of c is equal to 0. So if not, so if f of c is strictly less than 0, I have to get a contradiction. Now if f of c is less than 0, this implies that c is strictly less than b. Okay. So pictorially it means just this, that this is a, this is b, the value of the function is negative here, that means there is a neighborhood where it is negative. On b it is positive, that means there exists a neighborhood where it is positive. So c is somewhere here maybe. Okay, fine. That means if fc is less than 0, then by continuity of f, as I already said, there exists a delta bigger than 0 such that f of x is less than 0 in the whole neighborhood of c. What does that mean? So consider then c plus delta by 2. Now c plus delta by 2 belong to the interval c minus delta, c plus delta. This implies that f of c plus delta by 2 is also less than 0, because I said that f of x is less than 0 for all x in the interval c minus delta, c plus delta. Okay, but then this implies c plus delta by 2, it belongs to E by my definition, because E consists of all the points where f of x is less than 0. It seems that then c plus delta by 2 belongs to E, but then c cannot be the supremum, as c plus delta by 2 is strictly bigger than c, then c cannot be supremum of E. But this is a contradiction, because we know C is the supremum. Why did this contradiction happen? Because I have assumed that f of C is strictly less than 0. That cannot happen. But I already know that f of C is less than or equal to 0. So this implies what? It implies that f of C is equal to 0. Okay. Now let us see some applications of intermediate value property. So first application. Consider a function f from 0, 1 to 0, 1, which is continuous. Okay. I want to prove that then there exists x naught in 0, 1 such that f of x naught is equal to x naught. Okay. Pictorially it means just this, that first consider 0, 1. This is 0, this is 1. You consider 0, 1 here. Look at the square. Now the graph of the function lies between this square. That is what this condition says. Okay. Then the assumption says that if you look at the diagonal, which is the line, this is the line y equal to x, then the graph of the function at some point has to intersect this diagonal. It can be this, it can do it several times, but it has to. Okay. So how does one prove it? See, there are two obvious cases. It can happen that f0 equal to 0. If f0 equal to 0, we are through. That means I can take 0 to be equal to x naught. If f1 equal to 1, again we are through. Okay. Now the third case is when this is not true. What does it mean to say that this is not true? Notice that these two are not true implies that f of 0, since it has to be in the closed interval 0, 1, but it is not 0, that means it has to be strictly bigger than 0. At the same time, I am also saying that f of 1 is not 1, but it has to be in the closed interval 0, 1. That means the possibility is then f of 1 is less 1. Both this has to be true, right? If none of the above happens. Okay, so this is the assumption now I am working with, that f of 0 is strictly bigger than 0 and f of 1 is strictly less than 1. Okay, very good. Now I define another function, call it g. So I define gx as fx minus x. The purpose of considering g is very easy. It is just that I have to show that at some point x naught, g of x naught is 0. Just notice that g of x naught equal to 0 implies f of x naught minus x naught is equal to 0. This implies f of x naught is equal to x naught. This is the motivation to construct the function g. Now what do I know about g? G is a function from 0, 1 to r. That is obvious because I have defined it for x in 0, 1. Also the important thing is that since fx equal to x is a continuous function and the given function f is a continuous function, the difference of two continuous functions is always a continuous function. That's why the function g which I have defined, that is also a continuous function. Okay. Now notice, what about g0? By definition this is f0 minus 0. But I know that f0 is strictly bigger than 0. That means this is bigger than 0. What about g1? This is f of 1 minus 1. But I know that f of 1 is less than 1. That means this is less than 0. Now I am in the setup of the previous theorem. G is a continuous function defined on 0, 1. At 0 it is positive, at 1 it is negative. That means at some point g has to be 0 by the previous result. That this implies there exists x naught in 0, 1 such that g of x naught is equal to 0. And this implies, as we have observed before, that f of x naught equal to x naught. This is precisely what we wanted to prove. Now let us see some more important applications of this result. The first one is the following. Suppose I take a number x which is bigger than 0, and let us take a natural number m in n. I want to understand the meaning of x to the power 1 by m, called the mth root. See, the point is, we want to talk about mth root is that we don't have the precise definition of real lines with us. We are trying to develop it without going into the detail of the definition of real line. And once you do that, then several questions arises. Things like, what do you mean by square root of a real number, cube root of a real number, and so on, because the precise definition of real number is not there. But we want to show that something like x to the power 1 by m should exist. And this is where you will see that things like supremum axiom and whatever we have developed will come handy. It will give you the existence of some such things. Let us see how do we do that. So look at the function defined by f of y equals to y to the power m. The function is defined for f from 0 infinity to r. Okay. So what do I want to show? I want to show that given a real number x, I can talk about x to the power 1 by m. Okay. So if x to the power 1 by m equals to y, this would then imply that x equals to y to the power m. That motivates the definition of the function which I am looking at. Okay, good. Now concentrate on the function fy equals to y to the power m. Since this is a polynomial function, I know that f is continuous. Okay. Now x is given to me, x is bigger than 0. Okay. I am just saying that choose b such that b to the power m is bigger than x. That can always be done. And then I concentrate on the function f from 0b to r given by f of y equals to y to the power m, which is continuous. Now all I want to use is the intermediate value property. Since I have this condition, this implies that we have f of 0 less than x less than fb. Then this implies by the intermediate value property there exists y in the closed interval 0b such that f of y is equal to x, which implies y to the power m is equal to x, which implies by definition y is the mth root of x, and that is what we wanted to show. This y is actually called, this is the definition, y is called x to the power 1 by m. Right now, before the proof of this, there was no definition of x to the power 1 by m. So we defined the mth root of x to be equal to some y such that y to the power m is x. And when I want to show that mth root of a real number exists, all I need to show is that there exists an y so that y to the power m is x, which I have shown by intermediate value property. That means mth root of a positive real number exists. But here, while doing this, I have used the statement of the intermediate value property, which I have not actually proved. I have proved a special case of intermediate value property, that is, if I have a continuous function which takes positive value at one endpoint and negative value at other endpoints, then 0 is also a functional value. But that is not exactly the statement of the intermediate value property as we stated. So now let us try to prove intermediate value property from the result which I have already used. Okay. So now I come to the proof of IVP. So what does it say? That f is from AB to R and is continuous. Suppose FA is less than FB, and also suppose there exists a C which satisfies FA less C less FB. Then I want to prove that there exists X naught in the closed interval AB such that f of X naught is C. Well, while doing it, I will use the result which I have already proved. So I define a new function gx, which is fx minus c. Okay, the idea is very clear. I want to prove that this function g has a 0. That means there exists an x naught where g of x naught is 0. Once I prove that, it will follow that f of x naught is c. That will solve the problem. So first look at what is g of a. This is fa minus c. But since c is bigger than fa, this is less than 0. Now if I look at g of b, that is f of b minus c. But since I have that fb is bigger than c, what I have is that this is bigger than 0. This implies there exists x naught as g is continuous such that g of x naught is 0. Notice here that I am using the fact that g is continuous. But g of x naught is 0 implies f of x naught minus c equal to 0, which implies f of x naught is equal to c. This is precisely what we wanted to prove. Okay. After finishing intermediate value property, let us look at another example. It says there exists x in R such that x equal to cos x. In fact, I can rephrase it by saying there exists x in 0 pi by 2 such that x equals to cos x. How do we solve this problem? The idea is exactly as in the previous results. I have to show x equal to cos x. That means I have to show that cos x minus x is 0. To prove that for some x in 0 pi by 2, cos x minus x equal to 0. This immediately tells me that I can now look at the function gx equals to cosine of x minus x. And then let us see what is g0. That is cosine of 0 minus 0, which is 1, and that is strictly bigger than 0. And what is g of pi by 2? This by definition of g is cosine of pi by 2 minus pi by 2. But cosine of pi by 2 is 0, so 0 minus pi by 2, which is minus pi by 2, which is less than 0. Notice that g again is continuous. Then this implies g must have a 0. This implies there exists x naught in 0 pi by 2 such that g of x naught is equal to 0. This implies cosine of x naught is equal to x naught, and this is precisely what we wanted to prove.